Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our Q&A session. And today's topic is an extension from the previous topic. The previous topic we talked about water breakthrough using Sobocinski and Cornelius method. And the extension of the previous case is actually now we need to approximate the critical oil flow rate. Okay, so this is the problem, this is the case. We will maintain all the reservoir properties the same and other parameters also like, oh no, not oil flow rate. In fact, we need to find the critical oil flow rate, okay? The other will be the same, the density of oil and then permeability, the horizontal permeability, and then the reservoir thickness, also the fluid properties like oil viscosity, and then oil formation volume factor, water density, and then everything will be maintained. Okay. And now it's very simple. We just need to find the critical oil flow rate. Okay. But what is the critical oil flow rate? In terms of water conning issue, critical oil flow rate is the flow rate at which the water starts building up the cone. Okay. So this is the exact flow rate at which we will start making the cone. Or in other words, this is the maximum flow rate, right? The maximum flow rate where we will not have water conning. Okay, so you can see from positive or from negative perspective, all right? But one definition that we want to apply here in this case is this is the maximum flow rate at which we will not have water conning. Okay, so we will see that actually the flow rate will be quite low and maybe the critical flow rate will not be economical oil flow rate. This is the case, this is most of the time oil flow rate, critical oil flow rate is too low. So yeah, people will produce above the critical oil flow rate. Okay, of course you will have faster water breakthrough, maybe early water breakthrough, but they allow that because they need to boost the production. Okay, but it's topic from another day. We just need now to calculate the critical oil flow rate. Okay, so you see, this is the solution about the water breakthrough. All right, this is we talk about it. And now let's just go to the solution for the critical flow rate. I maintain the data table. Okay, I recommend you to do so. Okay, to make the data table for yourself for any case, maybe from the book or from the field, so that you will have your own spreadsheet to be used every day. Okay, so let's see the solution. So according to Joshi, yeah, Joshi observed the method, the Sobocinski-Cornelius method, and he checked this formula to calculate the dimensionless water breakthrough time and also dimensionless cone height. Okay, he checked it and he arrived at the conclusion that if Z is 3.5 or greater, there will be no water breakthrough. Okay, or in another way to say it, we need to find the flow rate to achieve Z of 3.5, and we will call that flow rate the critical oil flow rate. All right. So critical oil flow rate is the flow rate that will give us Z equals to 3.5, okay? Or the flow rate at which level we will not have water breakthrough. Okay, and by looking at this statement, we can see that the greater the Z is, the better the condition for us to have no water breakthrough. And we can have high Z if, for example, we have a low oil flow rate, right? If you have small denominator, you will have big Z. You can also have big Z, for example, if you have high density difference between the water and oil. Okay, so let's say water is so heavy, so much so you will not have water cone. Okay, and also if the distance or if the gap between the reservoir thickness and the perforated interval is so heavy, it's is so long, right? Or the reservoir is so thick, you will have great Z, you will have high Z. Or if you have very viscous oil, very high viscosity, okay, you can also have, high value of Z. Okay, so the concept is like that, but the method, the formula is very simple. Let me borrow this, for example. Let's just calculate it. QC or QOC, whatever you like. And this will be stock chamber per day. So let's just calculate it. 0.141 e to the power of minus 4 multiplied by density difference minus oil density multiplied by kH, horizontal permeability multiplied by thickness multiplied by difference between thickness and perforated interval. So let's multiply it first with the horizontal permeability and then the oil column thickness and then the gap, the difference between oil column thickness, the reservoir thickness minus the HP, perforated interval. Okay, I will put everything inside parentheses. That's our numerator, and then let's divide them with the denominator, which is oil viscosity multiplied by oil formation volume factor. Very easy. It's like this, and then I will close, and we have it. Okay, so the critical oil flow rate is 46.5. Okay, depending on your company, this value can be considered low or high. But of course, this is far lower than the operating flow rate as the base case, which is 250 to 150 stock chamber per day. Of course, we will have water conning at this flow rate, and eventually we will have water breakthrough. Maybe you can call it early water breakthrough at this flow rate, but it gives you high production, it gives you high revenue, but it also gives you water production. On the other hand, you will have low production, low flow rate, but no water production. So it depends on your management, depends on your economic analysis, but from technical point of view, from technical perspective, we have completed the calculation of the critical oil flow rate. Okay, so that's very easy. This is the flow rate at which we will achieve Z equals to 3.5. This is the flow rate at which we will just start making or generating the water cone, or this is the maximum flow rate where we will have no water coning. Okay, and you can also say this is the flow rate where there will be no water breakthrough. Of course, from theoretical point of view, not the real world point of view. Okay, and that's it. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching, and see you again in the next Eng-Man videos. Thank you.